continue on this discrete probability distribution, we want to look at a specific probability distribution, a discrete probability distribution called binomial probability. And there are so many different models for modeling different situations, right? Different type of random experiment. I've mentioned this because this is a kind of model that we can use for many examples that I've shown you in the class. Right? What is binomial probability? Okay. Now, if you recall, this is actually casting die experiment. All right. If I roll a balanced die 5 times, if I ask you what's the probability of getting 2 6s, how do you calculate that? I think I mentioned that. Okay. Now, we know that, well, if you cast a die 5 times, if it is a balanced die, right? Well, either balanced or not, what's the probability of getting 2 6s? Now, this is one of the possibility of 2 6s. The S stands for a 6. S prime stands for S complement, which is not a 6, right? So this is one of the events that is first time you cast that die, you get a 6, and then you get a 6, and then not 6, not 6, and not 6. So this is one of the situation. Now, every time you cast that die, the chance of getting 6 is 1/6, right? Because 6 is just one out of those 6 outcome. Okay? And after you perform casting a die experiment just one time, next time you cast that die, the chance of getting a 6 still 1/6. Okay? So it will not affect, whatever happened earlier, it will not affect what happened next. So these events, these outcomes or these events are independent to each other. Remember, we talked about independent events. If you have independent events, this could look like 5 independent events, right? If all these events are independent, what's the probability of intersection of all these 5 events? It's just a product of their probabilities, okay? Probability of S is, or 6 is 1/6, probability of another 6 is 1/6. So we have 2 factors of 1/6, 1/6 raised to the 2nd power. Probability of not getting a 6 is 5/6. There are 3 of them, so 5/6 raised to the 6th power, right? Or you say 5/6 times 5/6 times 5/6, right? This gives you the chance of this event. The first 2 times you get 6, and the next 3 times you don't get 6. But there are other possible outcomes that are 2 6s, right? You could have that first time is 6, and then not 6, and then 6, and not 6, and not 6. That's another situation. What's the chance for that to occur? Well, you have 2 factors of 6s, right? Probability of 6. And 3 factors of probability of 5, 6. So the chance is the same. These outcomes, the chance of them to occur are the same. Okay? What about this one then? First and fourth. Well, still the same, right? Probably it's still the same because you have 2 6 and 3 not 6. Chance of 6 to occur always 1/6. Chance of not 6 to occur is 5 6, right? With that multiplication rule for independent events, remember, probability of 6 and not 6 and not 6 and 6 and not 6. It's the probability of 6 times probability of not 6 and probability of not 6, right? So you will have 2 of those 1/6 and 3 of the 5/6, again, multiplied together. So all these 3 things have the same probability. Are there any other situation that satisfy the 2 6s? Yes, right? How about first and last? Okay? How about the second and the third? There's so many of them. How many of them? How many possible outcomes that are 2 6s? There are 10 of them. Okay? You can list them all, or you can use the combination formula to figure it out. Okay? And how do we fix this problem or do this problem? Let me show you very quickly to kind of remind you the counting technique. Okay? So I'm talking about casting a die 5 times. So I'm going to consider that there are maybe like 5 dice. It's the same thing. Okay? This is first, this is second, this is third, this is fourth, this is fifth. Now, this is one of the situation. Okay? If I have 1 and 3 that are S and these other are S complement, that's another, right? Or 1 or 4, or 3 or 5, or 2 or 4. All right? So any combination of 2 numbers, all right, 2 positions, if you let them be 6 and the rest of them are not 6, that's a different outcome. So you do realize that this, to solve this problem, really, we can use a combination of 5, take 2, right? How many possible ways can you select 2 numbers out of those 5 numbers? Okay, it's the same thing. Okay, that's one way to do it. There are other ways to do this counting, right? But I can use a combination formula. So, and if you do this, that's a 5 factorial, 2 factorial, and 5 minus 2, that's 3 factorial, right? So that's a 5 factorial, 5 times 4 times 3 factorial, 2 factorial is 2 times 3 factorial. 3 and 3 cancel, so 20 divided by 2, that's 10. So I can find out that totally there are 10 of these situations. Each of them have the same probability, right? So I use 10 times each of those probability. I get the exact probability of having 2 6s, okay? And that process is kind of tedious, and you need to know your counting techniques, right? Now, so why do we need to learn this binomial probability model? Because if you know that, you can solve any kind of problem without remember or knowing these counting techniques. Okay, so let's go back to this. Now we know that we have all many possible situations, and there are 10 of them. Okay, this is another notation for C52. Okay, in a lot of books they use this parenthesis and n on the top and r on the bottom. Okay, this is combination 5 takes 2. That's another notation for it. We call this binomial coefficient. Right? You might have learned this in algebra, right? The basic algebra. So you find out that there are 10 of them, and 10 times this number, you get the probability of having 2 6s. Right? This is based on the independent of events, so you use the multiplication rule, right? And to figure out the probability of one event, but all these 10 events, they're all the same outcome, right? 2 6s. And so you use a combination formula too. So combining counting techniques and then independence of event, you've solved this problem. And it looked kind of tough, and you probably can't remember that. Okay, but you do notice that to calculate this, you did need that combination of the 10 possible combination times. This is a probability of getting 6 raised to the number of 6 what we should see, and time the probability of not getting 6 raised to the power of not getting 6. Okay, now we can kind of organize it in this formula. This is called binomial probability mass function or probability function. Okay, it's a formula that we can calculate any kinds of probability probability for any kind of event in a binomial experiment. What is binomial experiment? Well, according to my definition here, it says the binomial experiment involving n independent and identical Bernoulli trials. So you wonder, what is Bernoulli trials? We've been talking about Bernoulli trial all the time. What is Bernoulli trial? When you perform an experiment, there's only 2 possible outcomes. That's a Bernoulli trial. Okay, so flip a coin, you're head or tail. That's a Bernoulli trial. Cast a die. Are you interested in seeing 6 or not 6? That's a Bernoulli trial. Or observing a person to see whether this person is sick or not. That's a Bernoulli trial. Right? Checking a product, whether this is a defective or not defective product. That's a Bernoulli trial. Am I making sense? As long as you have a random experiment that you only have 2 possible situations. And usually we categorize these 2 situations as a success or failure. Success means you observe the outcome of interest, right? Like head turns up. That's a success, right? Or observe a 6. That's a success. Okay? And binomial experiment actually involve an independent and identical Bernoulli trial. Means you're going to flip that same coin. Identical means what? The probability distribution stays the same. Flipping coin, it's always 50-50%. And you're casting a die, better be a balanced die, so the chance of 6 to occur, always 1 6. So every time you perform that experiment, the chance of 6 or success or occur and failure occur stay the same. So you're doing the identical binomial Bernoulli trial. Independent means each time you cast that die, after you've done that, next time you cast a die, right, it will not be affected by the previous trial. So they are independent. So casting a die several times, that's a binomial experiment. Okay? And of course, in this kind of experiment, we're interested in observing a certain number of successes, right? So say we're interested in seeing 2 6s, right? Or casting a flip a coin 10 times, we're interested in seeing 3 hats, right? What's the probability of that? It can all be solved by using this formula. In this formula, I have used some notation, right? Let's say in the binomial experiment involving n Bernoulli trial, n is the number of trials. Here, if you talk about casting a die 5 times, this n will be 5. Okay? And Bernoulli trial, each with probability of success p. This p is probability of success in each Bernoulli trial. So if we're talking about casting a die and interested in seeing 6 to occur, then this p is chance of 6 to occur, so that's 1 6. That's this p. Okay? And the probability of having x success can be calculated by this formula. X success is really that x that we define in event. We're interested in seeing 2 6s, then this x will be 2. Right? This is the event of interest that we'd like to calculate the probability for. Okay? Now, So this probability mass function actually can help us to calculate probability for any kind of outcome. You're interested in seeing no successes, no sixes, all right? Or 1 6, or 2 6, or 3, or 4, or 5 until n. N means a total number of trials, right? If you do it 5 times, right, the n will be 5. So we can figure out what's the chance of getting 5 6s too by using this formula. So notice that if you look at this formula, there's 3 different things that we need to know. We need to know the event, though, right? How many 6s we're interested, right, in finding the probability. We need to know exactly how many Bernoulli trials we perform. And we also need to know the probability of success in each Bernoulli trial. Okay? For that previous problem, this x really is what? We're interested in seeing 2 6s, right? So x should be 2. Okay? We're talking about casting a die 6 times. So n is 6. Each time we cast that die, the chance of 6 to occur is 1 6. So p is 1 6. Now, if I flip it back to this formula, isn't it just the same? N is 5, x is 2, you know, and n minus x is 3. This is a p raised to the x power 2, and this is 1 minus p raised to the n minus x power, right? If you look at this formula, okay. People try to solve this problem and realize, wow, we can actually come up with a formula like this to generalize it so that you can solve any kind of problem related to this, any kinds of event. Okay, let's see how we use this. Okay, yes.
Your probability, your uppercase P, then you have parentheses, uppercase.
Okay, this is a notation.
That's
This
a
P,
notation.
okay, good question. This cap P parenthesis, this is a notation for probability. Okay, here denote that the probability of an outcome is equal to this value. And what would that be? This is a formula to calculate. Excellent question, right? You got to know the notation. We've been using this kind of notation, cap P and parenthesis, to describe or to denote a probability, right? But this time, I use this notation, x equal to x. That means outcome. This lowercase, x means the outcome of a random experiment. Little x is the actual outcomes of interest. Okay? Sometimes people use the term random variable, right, for this cap letter x, denote the random outcome in the random experiment. But we're interested in the random outcome that is equal to this particular value. How do we calculate that? This would be the formula. Okay? Let's see another example. Okay. Well, before we do that, maybe let me show you this. Earlier, we learned what is discrete distribution. We know that for discrete distribution, we can find the mean and the variance for a discrete distribution. Okay. Now, once you can come up with a mathematical model to describe the discrete distribution, usually you can also find a formula, more nice-looking formula, to find the mean and variance for that particular distribution. Okay. For binomial distribution, the mean is actually n times p. N is number of trials. P is just probability of success in each trial. Okay, so you don't have to go through those formulas like using value times probability, add them together. It's all been done and simplified to a nice looking formula like this. So if I have a binomial distribution and like probability distribution, I like to find its mean. As long as you know n and p, you know its mean. You don't have to do those sum of products. You don't have to do that. Variance is n times p times 1 minus p. Okay, that's the power of those mathematics, in fact, right? You use mathematical function now to describe a probability distribution. Okay, because of that, you can make the life easier, right? When you calculate mean and variance, it's much easier. Of course, the standard deviation will be the square root of variance. So standard deviation will be just taking square root of this, right? That would be sigma will be square root of this, right? You know that. Okay, so let's look at an example, right? This question says, if there are 10% of people in a community have disease, what is the probability of 4 people in a random sample, 5 of this community that have the disease? Okay. So I'm going to take 5 people from this community. And this is a huge community. And we know that 10% of this community has certain disease. Okay. We're going to take 5. Is this a binomial experiment? Every time, well, the experiment will be like this. I'm going to select a person, randomly select a person from this population, and then check whether this person have disease or not. Okay, and then select another one, right? And I'm doing this without replacing means what? Select a one, and I won't put it back into the pool, right? I just set it aside, and then select another one. Every time I do this, the chance of this person have disease is what? 10%. So that's identical Bernoulli trial, almost identical. Although the whole population is one person short, right? So supposedly it'll change that percentage, but because of the population is too large, so that percentage stay around 10%. Okay. Usually we say they are almost independent. Okay, and that is good. We can still use this formula to solve the problem. Okay, so it's a sequence of Bernoulli trials now, right? Right? Do you believe me? Okay, and they're independent to each other. This time you select a person that it has a disease or not would not affect next time you select a person whether this person has disease or not. Okay, now, so I can use this formula to solve the problem because I know that this is a binomial experiment. Okay, now for doing binomial probability, I need to know what is n and x and p. What is n here? N is the size of the sample. How many trials? 5. That's right. What is P? P is at 10%, right? What is X? X is actually an event of interest, right? We're interested in seeing 4 success. So X is 4, right? So once you got this number N is 5, X is 4, probability of success is at 10%, and just plug it into the binomial probability formula. N, X, this is N minus X. This is P raised to the X power, 1 minus P raised to the N minus X power, okay? Then, of course, then you want to use your calculator to calculate all these, and you get 0.0045. Okay, so that probably is very small. If, in fact, your population, there are 10% in the population that has a disease, the chance of a random sample of 5 that observe 4% have the disease is very small. Okay? And to solve this problem, you don't have to go back to the independence of event multiplication rules and the counting. You don't need to because you realize this is a binomial experiment. You can use this function to help you to calculate probability. And life will be much easier. Okay? Let's look at another example. Similar setting, but what if I ask you what's the probability of having 4 or more people have the disease in a sample of 5? Okay. Well, if you do that, that means what? Actually, you're interested in the outcome that is greater than or equal to 4. Okay? That is what? If you can find the chance of 4 people have disease and 5 people have the disease and add them together. There's no other if possible outcome. 4 or more, that means 4 or 5 because the total sample is 5, right? You cannot have more than 5. Okay? Then what you do is calculate the probability of getting 4 and then probability of getting 5. Probability of getting 4, we already got it, right? Probability of getting 5, simply just n is 5, and then r is 5, or x is 5, right? N minus x is 0, and then p raised to the x, 1 minus p raised to n minus x, okay, and calculate it. You get a number that is 0.00, it's about 0.00046, and that's still a very small number. Okay, does it make sense? Kind of? Okay. Now, what's the meaning of this number? This number is very small, right? In fact, this number is a so-called p-value, right, that people use in statistical inference. Now, the setting or this research study could be like this, that people made a claim that there are 10% of the population that have a certain disease, disease A, okay, and you don't believe that. So what you want to do, you go out and take a random sample. So you observe 5 people. And you observe 5 people and you come back and you find out 4 of them have the disease. Well, if it's 10%, right, if you take 5, about half a person have the disease, right? Or if you take 10, about 1 people have the disease. 4 is really too much. How likely would that occur? This actually tells you the probability of observing 4 or more people have the disease, right? Given an assumption that 10% of the people have the disease. What's the chance of that? Very small. But when you really go out and take a sample of 5 and you realize this happened, this really unlikely to occur event happened, that suggests that your claim is not likely true. So that's how statistically we make decision. Okay? This is probably too small based on the claim. So we're going to reject the claim because this is our evidence, right? This is what we actually observe. Some people say, well, there's always that sampling error. Sometimes you get more, sometimes you get less. Maybe next time you get sample of 5, you get 0. That's possible. Okay? But this actually evidence actually occur when you take first sample. Okay? And usually when you do your research, you're only allowed to take one sample, right? If you're allowed to take two samples, you would just put them together, make it a larger sample. Because usually our common sense tells that the more information you get, the better. Okay? So if we only have 5 people, some people say 5 people is too small a sample. Can I make decision? Yes. In this case, we really can make decision just based on 5 people. Okay? And this is what I said, p-value. Remember yesterday, I mentioned the term p-value too when we do normality tests. Okay? This is another place that we can use p-value. And a lot of times people use 0.05 again as a cutoff. This probability is so small, smaller than 0.05, I'm going to conclude that the claim of 10% is not correct. Okay? And that's usually how people make decisions. Later on, we're going to come back to this and formally introduce the procedure stepwise, right, for you to do these hypothesis testing. This is just give you a concept, right, the idea of testing statistical hypothesis. Of course, in the beginning, you have to have a research statement or claim, right, or hypothesis. And you collect data to prove or disprove these hypotheses. Okay, good. Now, the same setting, with that probability mass function, I can actually calculate the probability of 0, right? Nobody have the disease, or 1 person have disease, or 2, or 3, or 4, or 5. I can calculate them all. And if you add this up, it should theoretically add up to 100% or 1, right? But because of some runoff error, I don't really have the 1 there. Okay, but it should be very close to 1 with the runoff error. And I can actually do a probability bar chart for it to see the distribution pattern. Now, if this is the case, the chance of a person have disease is 10%. If you take 5 people, right, then among the sample of 5 people, the chance of no one have the disease is pretty high. Okay, the chance of having 1 person have disease is this, 2 is this, 3 is this, 4 and 5 is almost 0. Okay, so with that probability mass function, it actually describes the whole thing, right? Everything related to that binomial experiment. That's the power of this, mathematical modeling technique. Okay, and this model is called binomial model. Of course, there are other type of experiment. There are other models to deal with those, right? This just gives you an idea. Now, in using mathematical model, right, you'll be able to simplify the whole process of getting probability or understand the outcome from a random experiment. Okay, there are theory behind this, though, right? But we kind of know. Well, we kind of know the theory already, right? You know the multiplication rule based on independent of event, right? And you also know the counting rule. Okay, actually, we're using those to build this model. And you saw an example. That example matches this model very well. Okay. So go back to that example. We found out that this is a probability model. So it's a distribution. Okay. And this distribution should have a mean. Now, since we have a probability and the values, right? These are all the 6 possible values, and this is their probability. We can calculate a mean, right? Using the formula that we learned earlier, on Monday. We should be able to use a 0 times this, 1 times this, and 2 times this, and then add them together to get the mean. However, once you know this model, you don't have to do that. The mean should be simple. Remember just now I said mean should be n times p. So 5 times 10% would be 0.5. That's a mean. That's the expected value from this model. Which means if you randomly select a sample of size 5, you expect to see about half a person have disease. That's the expected value of that distribution, or mean of this distribution. Okay. So what if I increase this sample size to 10? What's the expected value for this distribution? 1. Which means if you take a random sample size 10, you expect to see 1 out of those 10 people have the disease. That's a mean value, right? Or if you are able to repeatedly perform such an experiment, take a sample size 10 and observe how many, and take a sample size 10 again, observe how many, and try to do this empirical study. And eventually, if you get the average, you'll find out that average number will be very close to 1, right? And I think that makes sense, okay? And the variance of this distribution can be calculated by n times p times 1 minus p, which is 0.45. So again, you don't have to use this definition of a variance for a discrete distribution to calculate. That would be too terrible, right? Remember yesterday, on Monday, I was trying to calculate it. I keep making mistakes, even I have that table. But with the model, if you do have a model that can describe the probability distribution for a random experiment, then solving the variance is so simple. 5 times p times 1 minus p. You got the variance. You don't have to use a 0 minus mean and square and time probability, or 1 minus mean square and time probability. That would be too tough. Okay? Am I making sense? Yes?
So this binomial probability is only used with these Bernoulli trials where there's
Yeah, when you have a binomial experiment.
success or failure.
Yes. When you have a binomial experiment, you can always use this binomial probability model to model that type of problem and to calculate any kinds of event. Okay? That's really, yes?
How do you distinguish if it is a binomial problem?
Well, remember just now, let me go back to that. If you have a binomial experiment that involves n independent and identical Bernoulli trials, okay, and you're interested in observing number of successes in the Bernoulli trial, that's a binomial experiment, okay? So I'm talking about casting a die and interested in 1 to occur, okay? And I'm going to do that 10 times. How many times turn out 1? Okay, this kind of model, this kind of problem can be solved by binomial probability. So 10 times, what's the chance of getting 5 ones? Well, use this formula. Okay, flip a coin 20 times. Well, you can solve this too. 20 times interested in seeing 5 hats. What's the probability of that? This formula can do. Okay, you don't have to build a tree diagram 20 levels. That's gonna kill you. Right? But with this formula, it's become easy. Does it make sense, Soro? Okay. There are other models that deal with different things. Right? There's a Poisson model that can model number of rivals of customers or patients to accountants or something like that. And you can model it with Poisson distribution. A lot of times people use that to model the outbreak of disease. Okay, and that's a different setting. So right? There are other models that deal with different situations. Okay, but I'd like you to know this. At least knowing one model, you will appreciate the power of mathematics. Right? That can help you to simplify the process of calculation of probability, or actually understand the whole thing, right? The whole probability distribution for a random experiment. Okay, let me see. Oh, is that all? Let's try another example. How about that? How about from the textbook? Binomial experiment is section 4. Okay. Well, there is a question that is about truth or false exam. They say you take a 20-question true or false exam, guess each question. All right, so you're guessing it. And since it's true or false, and you're guessing it, the chance of guessing it right is what? 50%. Okay, so it's like flipping a coin. But there are 20 questions. What's the probability of answering 12 of them correctly? So you kind of pass the minimum, right? Answer 60% of them correctly. What's the probability of that? You have 20 true or false questions, right? What's the probability of 12? Answer 12 correctly. The books say 15, so I'm using 12, right? That's you can go back and practice the 15. Okay? So how do you solve this problem? To answer 12 correctly. It's a binomial experiment, you know that, right? It's just you're every time you're doing guessing. Now, for doing binomial experiment, we need to know what is n, what is x, what is p in order to use that formula. What is n in this problem? 20. What is x in this problem? X is the event, right? How many successes? 12. That's right. What is p? P is probability of success, probability of guessing it right, right? 50%. So you got them all. What you need to do is just apply that formula. Remember that formula is n factorial, x factorial, n minus x factorial, then p raised to the x, 1 minus p raised to the n minus x. Okay? So to use this formula, what you do, 20 factorial. Oh, I'm in trouble then, huh? That's fine. 12 factorial, and this is what? 20 minus 12, right? 8 factorial. Then raised to the 0.5, the p raised to the 12 power, and 1 minus 0.5 raised to the 8 power. Okay, that's a little bit tough, right? 20 factorial, do you have a calculator? Can you calculate 20 factorial with your calculator? Can you? You can? There is a factorial, like there is a key like this. Right, if you use that key, internumerator that key, can you get 20 factorial? It's a huge, very huge number. Your calculator probably can't handle it, right? So what you should do then, you should actually make this 20. This problem is terrible. Maybe I make it easier. How about that, right? And then you will realize there's a bell-shaped distribution, no more approximation for binomial. That can help you to approximate this distribution without so much headache. How about make it 90%? My expectation now is higher, right? So answer 18 of them correctly. Then this will be what? 18. This will be 2, right? This will be 18. This will be 2 again. And because of that, the calculation will be easier, right? It'll be 20 times 19 times 18 factorial. And we have 18 factorial times 2 factorial, that is 2, okay? Then we have 0.5 raised to the 18, and then 1 minus 0.5 is 0.5 raised to the second power. Now this 18 and 18 cancel, this 2 and this 20 cancel 1, so it's 190 times 0.5 raised to the 18 power times 0.5 raised to the 20 power, 2 power. Actually, this is 119 times 0.5 raised to the 20 power, right? 18 and 2 power, second power, right? But if you're not comfortable doing this, just go ahead, do this, each of them, and use your calculator to find that out. And do you know that in your computer has a calculator too, right? If you notice. Computer has a calculator like this. If you go Start, All Program, Accessory, there's a calculator there that you can use. Okay, that calculator, actually you can view it. The simple standard calculator or scientific calculator give you more. Okay, either one. And there's a factorial there if you like to use factorial. Okay, but anyway, what I'm going to do is just 190 times 0.5 raised to the 20 power. Ooh, is that right? Huh? Do you have the same number? 0.000018. Okay. Right? 0.5 raised to the 20 power times 190. 0.000018. Okay. So I'm going to write down the answer. 0.00030. Sorry. Yeah, 18. So if I give you a true or false question, 20 question, right? The chance of scoring an A, or exactly 90% be this small. How about